So good evening, everyone. The title of my talk is Rejection-free Cluster Wang-Landau Algorithm for Hardcore Lattice Gases. This work has been published in this paper. If anyone wants to look it in more detail, can go through this paper. So let's first define what is a hardcore lattice gas. So this is a system of square lattice in which you fill a particle at a site, and the exclusion constraint and the constraint is depending upon the range of exclusion, you cannot fill further particles. Like here, the red circles define the first nearest neighbor exclusion, whereas whereas the second exclusion part is the green circles, and the third exclusion part is the circles labeled by 3. So depending upon the exclusion criteria, we have several models like 1NN, 2NN, 3NN in 2D and 3D, and they have different densities. And we see that at full packing, there is two kinds of ordering. One is sublattice and the other is columnar. So the algorithm that we use to sample this hardcore lattice gas, we have 3 algorithms. The older and traditional algorithms is the single site Wang-Landau algorithm and the unbiased strip cluster Wang-Landau algorithm. In single site algorithm, you update one single site at a time. Whereas in the unbiased strip cluster, you have a cluster and you want to fill the particles in the cluster. And in both algorithms, we have a new configuration that is weighted over the older configuration by minimum of 1 comma G annulled by G nu, where G is the density of states. But we developed a new algorithm, which is the strip cluster Wang-Landau algorithm, which is also a cluster-based algorithm. But here, the new configuration is weighted by the inverse of the density of states. And here, we don't discard any new configuration, and we evaluate all of them by any weight. Hence, this algorithm is called rejection-free. So Wang-Landau protocol is the way in which we can calculate the density of states for our system. And here in the algorithm, we have an initial condition on G of n, the density of states, and we continuously evolve it during the simulation. And it is expected that it will converge to its true value with increasing time. And we adopt a flat histogram technique where a histogram and entropy is maintained. So in the algorithm, during the simulations, we add the histogram by 1 and the entropy by parameter f, where n is the number of particles that are occupied in the configuration that is reached. So due to sampling by the inverse of density of states, the histogram will reach a flatness criterion to complete an iteration. And once an iteration is completed, we modify the factor f by f by 2 and reset the histogram for the next iteration. We repeat this iteration till f becomes smaller than a set value. So if we do that, we get an entropy for a system for 1NN model and from the 3 different algorithms that I mentioned. And then we compare it with the exact value. The entropy with the desired accuracy is pretty close to each other. So we have been able to reproduce the entropy from the simulations. And here for the 1NN model, we have an error function which is defined like this, where S of n is the numerically obtained entropy and Sxn is the exact value of entropy for that n number of particles. One can see that the strip cluster algorithm, the new algorithm we have, that have a better convergence compared to the blue and compared to the red and the green curve. And it also saturates to a value which is smaller than the other two. So the convergence is pretty good for our new algorithm. So this is another example from the 2NN model in which we plot the entropy of states for 3 different iterations, 5th, 10th, and 20th. We can see that the single site, SSWL is the single site algorithm. In this algorithm, we have actually the sampling is not proper for larger dense regions. It actually comes closer to the proper one only at the 20th iteration. Whereas the strip cluster Wang-Landau algorithm, the proper shape has already come from the 5th iteration itself. So the convergence is pretty good. So here we show another measure, which is the exit times. Exit times is the number of Monte Carlo steps taken for flattening the histogram. And here in this side, we have the 1NN model. And here we have the 2NN model. And in both the models, you can see that the blue curve is actually the least compared to the red and the green curve. And that also shows that the convergence to the histogram, convergence of the density of states to that actual density of states is pretty good for the strip cluster algorithm. So there can some applications we can do using the strip cluster algorithm for these models. So here we defined an observable, average observable to be this formula, where we get the G of n from the entropic algorithm, and On is the average number of average order parameter for n number of particles. And then one can define the compressibility, susceptibility, and pressure, where compressibility is defined from the variance of density. The susceptibility is from the variance of outer parameter, and the pressure, by knowing the entropy, we can calculate. You can also calculate a canonical ensemble pressure, which is defined like this, where phi rho is actually the mean number of sites that gets blocked during packing of the lattice. And then there are some transitions that we can study from these, like the continuous transition, so which scales like this. And here the compressibility, average order parameter, and susceptibility. L is the system size, alpha, beta, nu are critical exponents, and f chi, f q, and f chi, f kappa is the universal functions. So we also define another quantity, which is t, which is derivative of log of q by log of mu, derivative of mu. And this quantity is interesting because this doesn't depend upon, this just depends on one critical exponent, which is nu. So here we bring in all the results from the simulation for the 1NN model. And here we have plotted the t for different system sizes and the susceptibility for different system sizes and the average order parameter. And we can see that they collapse on top of each other for all the different system sizes. And if we plot the maximum of this t value and the susceptibility and the average order parameter, we can see a straight line in a log scale, and one can get the critical exponents. So the exponents that we get is 1, the nu is 1, the gamma by nu is 1.75, beta mu is 0.125. So we saw that this is actually belonging to the Ising spin universality class. Then the other model which we studied is the 2NN model. There also we have a continuous transition, and we see that the susceptibility, the t value, and the average order parameter scaling on top of each other. And then we can plot the maximum on a straight line and then get the exponents. So unlike 1NN and 2NN, we can also study the 3NN model, which shows a first order transition. So in the first order transition, we have a coexistence region where the pressure is flat, and the canonical pressure that we get is it also forms a loop-like structure. And then the interesting part is, in this coexistence region, we have an entropy which has a non-convex region, and the starting and the ending point of this non-convex region can be used to calculate the critical chemical potential. So here we have the critical chemical potential for different system sizes, and we can get the critical exponent for the system size at infinity by doing an extrapolation. And here also we have the scaling collapse of the susceptibility and the compressibility plot, but their scaling has L square dependence, which is like characteristic of first order transitions. So at the end, I can say that the new algorithm which we have is able to replicate the physical quantities that is there from a non-model. Thank you.
Questions?
So the transitions that you mentioned in the KNN model, they seems entropic driven, right? Yeah. So I just want to understand how they are related to symmetric breaking transition in Ising model or in the Potts model, something like that. So how they exactly belong to the Potts universality class? That's what I want to understand.
Yeah, so In 1NN model, we can do the scaling collapse and get the exponents out. So this exponents is mu equal to 1, beta by nu is 0.125 and gamma by nu is 1.75. These are exponents of the Ising class also. So we get critical exponents which are similar to that. So from that one can say that this is also belonging to the same universality class.
Yeah, but how they can be analog to the symmetry breaking transition that takes place in Ising or in the Potts model, something like that. That's what I want to understand.
No, I don't know.
Thank you.
Okay, if there are no more questions, let's thank the speaker.